And here we go. Okay, so Josh isn't here yet. Alice, you were not here last year. Is that true for chemistry? You were at Mountain View. And Cody, you were obviously at Timpanogos. So, guys, what we're going to do today is we are going to, well, let me say it this way. Do you remember how we started this unit and we paged through chapter 6 and we looked at the very beginning of chapter 6 and we talked about this idea that chapter 6 is all about electrons, right? And we said, hey, chapter 6 is about electrons, but when you turn the page, it's not electrons, it's waves and light and all of these intermediating ideas. And then we said that the chapter became perhaps more familiar where you finally got to like page 220, and now all of a sudden things became more familiar as you're starting to see the clouds and the S's and the P's and the D's and the F's and the energy levels and the sub-levels and the extra credit, right? Remember last year we had the and so we had this conversation that said, maybe you found that weird because you see chapter about electrons and you think this is going to be the conversation, but it's a different conversation. It's a wave conversation. Well, guys, now we're going to have this conversation. Here's the problem. I don't think TJ did much of this last year, did he? Like, do you look at that stuff and does that look familiar? It does. Alice, for you, put your phone away if you would, please. You look at this, does this look familiar? Okay, so guys, I want to help, and I will help anybody, whether you had me and Miss Call last year, or whether you had whomever taught this over at Mountain View or TJ at Timp, because you're walking into this with a lot of different backgrounds, but because this is a group, I'm going to try to shoot for the middle. And guys, the middle is frankly the experiences that you had with Miss Call and I. But even at that, there's probably going to be gaps. Anytime you learn something for the second or third time, you're going to be picking things up. So guys, I am going to teach this as review. If this is not review for you, frankly, you may have some more work to do. I would be happy to participate in that work if you'll invite me into the conversation. But guys, we are going to get back around this idea of energy levels and sublevels and orbitals and spinning electrons. So, guys, with that said, if this does get a little bit muddled for you, I want to help. You just need to engage me in the conversation. So guys, when we talk about energy levels and sublevels and stuff like that, you don't need to know this, but this is actually all organized through something that are called quantum numbers. You know what? Let me do this. I think this is going to be faster to just print this for all of you rather than it will be to have you try to write this stuff down. So let me get rid of that. I'll just print it like this. There's what, like 20 of us? 1, 2, 3, 4, 5, 6, 7, 8, 16, 17, 18, 19, 20. Okay, that'll be cool. Let's go 22. Okay, so guys, let me just print this for you, and then we'll talk about it as we go. Would holes be helpful?
Yes.
All right, let's try this. You betcha. Okay, so guys, the conversation goes like this. So this entire page that you have in front of you now is really, in a lot of ways, all the information that we need in order to describe what electrons are doing. Now, guys, understand that this is in the same sense that all we really need is two numbers to describe where your house is located. Have you ever thought about that? That you can pinpoint the location of your house with two simple numbers. My address is 362 West, 700 North in Linden. 700 North tells you the street that you're on. 362 West tells you the lot that you're in. And so, guys, with those two numbers, we can actually pinpoint where any house is in Utah County because we're all on this awesome grid system that the pioneers figured out. Well, guys, understand that electrons are much the same. That if we want to know where electrons are, we need an address. And that address is made up of what are called quantum numbers. Now, guys, the first of these quantum numbers is what is called the principal quantum number. Now, guys, don't go passive. Get something in your hand. We're going to doctor these things up. First, and then let's talk about the things that you understand now that you didn't understand before. So guys, the idea is this. The principal quantum number tells you the size, and I would think that worth underlining, guys, tells you the size of the space that that electron occupies. And guys, realize, are you comfortable with this? When we say occupies, we mean highest probability of being there. Is that okay? That electrons don't really have position in that sense, that we're talking about probabilities of finding them. So when we talk about this, we're talking about the size of the energy level. So guys, maybe at this point, it might be worth drawing this if that's a representation that means something to you, meaning we're literally talking about the size of the cloud. Now guys, you may remember that these numbers actually range from 1 to 7 on the periodic table. Where do we find that 1 through 7 on the periodic table? Yeah, the rows. These are the energy levels on the periodic table, and we can talk more about that as we go. But then guys, the idea is that these energy levels, these clouds, if you will, we'll talk more. Guys, they have capacities. And the capacity is given by the 2n squared rule. Do you remember how to manipulate that thing? So we've got 1, 2, 3, 4, 5. Guys, these are the same numbers that we plug into the Rydberg equation, right, to find the energies. N is 1, N is 2, N is 3. But if we want to know the capacity for electrons, we can plug those numbers in here. And you square first. So the first energy level has can have how many electrons in it? 2. And then the second is 8. And then 8. Yep. And then 32. And then 50. Do you see where we're getting those numbers? So plug n in, square it, double it. 3 squared is 9, doubled is 18, and so on. Is that okay? Okay. So guys, then what we find out is that the electrons in those atoms, as n increases, the electrons in those atoms actually all increase in size. Are you okay with the idea? The electrons don't increase in size. Sorry, guys. The space increases in size. So we've got 1, 2, 3, 4, and so on. Is that comfortable? Okay, now guys, this one's interesting. The energy increases to a maximum of what? Come on, guys. You learned this in the last unit. 0. Right? So if we plug this into the Rydberg equation, remember I lied to you last time and I said 125, so on, right? And that went up to a maximum of 0, which means energy level infinity, and then that means no association with the nucleus. So guys, these are the energies that we're talking about. Gaining energy, gaining energy, gaining energy, gaining energy, losing energy. Those are the energies that we're talking about with these energy levels, and this goes to a maximum of 0, which means no association with the nucleus. You also know all of these are negative energies, which is weird, but the idea is that the negative gives us direction, like falling down a hole. Guys, these are the energies that we're talking about. You learned about this last year, but now you know so much more about it because we had the Rydberg talk last time. You okay on energies? Go ahead, Caleb. Velocity means the number of electrons it can hold. 2, 8, 18, 32, 50, and so on. So that is given by the 2n squared rule. So guys, the idea then is this. As we move into higher and higher energy levels, they get bigger, they get more energetic, and they can have more neighbors. More electrons can go in those energy levels. Anything you want to discuss there? Is that good? Okay. So guys, here's the idea. All of this right here, this is Bohr. Hey, Josh. Oh, here, let me give this to you before you walk by. It's our first page of notes. So guys, all of that information is associated with Niels Bohr. Was he wrong? No. He was absolutely right. Guys, all of this stuff was the Bohr model of the atom. But guys, if I ask you to draw the Bohr model of the atom on your paper, what would you draw? What do we call the Bohr model of the atom? Planetary model. You draw a nucleus and you would draw circles, right? And guys, that's where this conversation started. These were literally the circles that Bohr represented in his model. Now, he wasn't wrong. He just wasn't completely right. We still don't know that we are completely right. But guys, the thing that Bohr didn't understand is that these spaces were not spherical. They were not paths. They were, as we said, probabilities. And that's where Schrodinger came along. And he said, well, yes, these principal quantum numbers are valuable. We need other variables to describe the complexity that's actually going on here. And guys, this is where we start to talk about sublevels. So the idea is this. These energy levels are not just spheres. And Bohr understood that atoms weren't flat. He didn't think they were actually just orbits, but he thought they were spherical. Well, guys, it turns out that they're not. Always. So these energy levels are made up of sublevels. Now, guys, and the sublevel, the sublevel tells us the shape of the space that the electron occupies. So you might want to underline shape. So guys, this tells us the shape of the space. Now, what are our options? What does the S look like? Spheres. What do the P's look like? Dumbbells. Oh, this is cool. We have models. So guys, looks like this. This is pretty good. So guys, the S looks like this. The S's are spheres. The P's are these dumbbell shapes. The D's are these clover leaves that really get wacky. And then the F's are even more complicated with their lobes and their rings and all this different stuff. But guys, these are actually the shapes that the shapes of the spaces that these electrons appear to occupy as they're doing their things around the nucleus. They weren't just spherical, as Bohr thought. They were much more complicated than that, and that's where we needed people like Schrodinger to extend the model and give us a more complete idea. So that's where sublevels come along. So guys, energy levels are broken into sublevels. These sublevels tell us the shape. Now guys, what are the options as far as shapes go? And we've got the S, the P, the D, the F. And again, there are representative shapes, and we'll look at those in a minute. But then, guys, and maybe you remember this, you can't have an unlimited number of sublevels in an energy level. So the number of sublevels in an energy level is n. Do you remember what that means? Let's talk. So, guys, first energy level can have how many sublevels? 1. It's an S. Uh-oh. It's an S. Guys, the second energy level can have how many sublevels? 2. S and P. The third is 3, S, P, D. The fourth is 4, S, P, D, and F. The fifth is 5, S, P, D, F, G. Yeah, they're in theory, if we, and I used to do this for extra credit, predict the atomic number of the element that would be that would first occupy a G sublevel. But guys, we're way, way, way away from it. So after energy level 4, it's all just SPDF. In theory, if we ever see atoms this large, there would be a G sublevel. We actually know what they look like. Google it sometime if you want. Because remember, guys, these are all just mathematical models. It's actually what they do, but they're mathematical models, so we can solve it for G as well. Yeah, good. And so because you ask, we'll make the connection, but we were going to make it later as well. So the idea is this, that the first time that we see a D sublevel, that D sublevel actually begins to fill after the 4s. And so what you're going to see is, let me see, my board is being really weird, but I'm going to take a chance. So actually, you know how we've been doing this and we've been drawing this sort of thing and sort of drawing them evenly spaced? That's not really what this looks like at all. It actually goes more like this. So the first energy level would be like here, and then the second one would be here, and the third one would be here, and the fourth one would be here. I'm doing my best. They're always closing in on each other. And so the idea is that by the time we get out to the fourth energy level, there's so little space between the third and fourth energy level that the 4s sublevel actually encroaches on the 3D and they overlap. And so while in fact that D sublevel is a part of the third energy level, it fills after the 4s. So then we ask the question, why? And the answer is because a slightly larger sphere, the 4s, is lower energy than a slightly bigger crazy cloverleaf. And so consequently, that one fills first. Is that okay? You guys okay? All right, so guys, moving back then, what do? I'm scared to click, but I have to. This and this. Yeah. It's really killing me. Okay, so guys, are you okay with this idea of the number of sublevels in an energy level is N and S, P, and D? Okay, so now the question is this: what are the sublevels made of? And guys, the answer is orbitals. So the orbitals are actually the spaces that these electrons occupy. But it's important for you to keep track of the idea that it's 2 electrons in an orbital. And we'll work more with that in a minute. But guys, remember when I asked you the question, what does the S sublevel look like? What does the S sublevel look like? Sphere. That's the orbital. That sphere is the orbital. Guys, what does the P sublevel look like? Dumbbells. One of those dumbbells is an orbital, but how many are there? 3. So it goes like this. So this green guy, right? You've got one orbital that's up and down, one orbital that's left and right, one orbital that's in and out. So those green dudes are the orbitals, and the 3 of them together make up the S sublevel, or the P sublevel. Is that okay? Okay. So then, guys, the last thought before we move past this is we've got a problem. Because what we're saying here is that electrons pair up in an orbital. And guys, that shouldn't happen, because what do electrons do to each other? They repel. And so how do we account for this idea that electrons are pairing up in an orbital? And guys, the answer is spin. Do you remember the idea behind spin? So if you don't remember, the idea is this. So my fingers represent electrons. What are their charges? Negative, so they repel, right? But guys, the other thing that you need to know about electrons is they have north and south poles. They have magnetic properties just like the Earth and just like bar magnets. And so when electrons come together, what they will do is one of them will actually orient itself opposite the other so that their north and south poles are out of phase with each other, and that slight attraction allows them to overcome their negative repulsion, and it allows them to pair up in an orbital. Now understand, when they pair up in an orbital, it's not like they lock together and then run around together. They are still in fact separate. Like if you've got a p orbital, one will tend to be up here and the other one will tend to be down here. If you're in an s orbital, if one's here, the other's there. So they do still spread apart, but they don't fly apart because of that magnetic attraction. So guys, we describe that attraction as spin. So the idea is that electrons actually do kind of spin. And we can actually detect the direction in which they are spinning. And as they spin, when they pair up, we can actually detect that they're spinning in opposite directions, meaning that their poles are out of phase, showing us that they're north to south oriented. So guys, that was a lot of information. Anything there you want to explore? Because what we're going to do for the rest of the day is build on this and kind of flesh out this idea of what atoms actually look like. So you guys okay? You're good? Okay. So guys, here's what I want you to do. I would just do it on here. Grab this sheet of paper I gave you, flip it over on the back. So maybe we should pause and ask, Cody, is this okay so far? So TJ got to this? Alice, Mountain View, kind of. Josh, Mountain View, okay? Kind of? Okay, all right. Well, and maybe guys, the rest of you, I know, have at least seen this material because I lifted this slide right out of general chemistry from last year. Doesn't necessarily mean that you understand it, though. So there are things there that you want to drill into? You feel like you're on an okay foundation? Okay, so guys, with that said then, here's what we're going to do. On the back of your sheet of paper, and if this starts to feel amazingly familiar, oh, there it is. So guys, do this. On the back of this note sheet, right down here at the very tippy bottom, write the letters NUC for nucleus, and then draw the ladder. Now, I'm wondering, you know what I'm going to do? Guys, I want to go back and get this out of my general chemistry slides because I changed this a little bit in Gen Chem. And I like the way that I did it better later. Hey, look, there's all the stuff from general chemistry. Oh wait, this isn't it. Sorry. Okay, let's try this again. So guys, down there where you wrote nucleus, draw a half circle over it, indicating that it is actually a sphere. Then guys, from there, don't write this down, but this is the idea. If you remember a second ago what I was trying to explain to Bailey or show Bailey is that this is not the reality, that these are not evenly spaced around the nucleus. Instead, it actually looks more like this. Guys, we're going to represent that reality with this discontinuity symbol that shows us that if this were to scale, guys, the place where you drew that nucleus would actually be down on first floor. That's literally the scale that we're at. That in order for this to be to scale, that nucleus and the distance between the nucleus and the first energy level would be like unto the nucleus being 2 floors down. Obviously, we can't represent that and still get the detail up here that we need. So there is a discontinuity. But do notice this. These rungs are closing in on each other. So we've got the first, second, third, and fourth energy level. And guys, we are going to number those then, and they go 1, well, energy level, sublevel, orbital. Like so. You guys all caught up? So, I'm debating. All right, I'm just going to show you. So, guys, what are we looking at here? To help you wrap your arms around this model, guys, what we're looking at here is a core sample. This is a core sample of an atom. And if you're not familiar with the concept of a core sample, what we're talking about is this. If you take an apple core and rip the core out of an apple, if you drill to the middle of an apple, and then if you rip the core out of the apple, guys, by looking at this, you can see what's in the middle of the apple, and then you can see the layers that then make up the parts of the apple. So you've got the core, you've got the edge of the core, you've got the edge of the flesh, you've got the stem. So by drilling down into something and removing it, you can then see what's inside of something like an apple. Well, guys, similarly, that's what we are doing with an atom. So if we think of an atom as being a series of cloud-like spaces, if we drill into this and then pull this out, we then end up, I don't know why it skipped like that. Guys, if we drill into that and then pull this out, you can see that what we've got is we've got the core, and then we've got these layers that represent the rungs. Do you see how that applies to what you have on the paper in front of you? Okay. All right. So guys, what we can do then is we can take this understanding of this core sample and we can bring this are doing around the nucleus of the atom. So guys, what do these rungs represent? The energy levels. And so let's label them, let's number them. They are actually numbered then, moving from bottom to top, 1, 2, 3, and 4. This should go up to what? Should go up to 7, but guys, we're only going to do the first 4. Now, in order for this to make sense, the next thing that we need to do, and I'm going to shut out the lights so you can see better detail. Guys, the next thing we need to do is figure out how many electrons can be in these energy levels. So how many electrons goes in the first energy level? 2. And in the next one? 8. And then in the next one, 3 squared is 9, double that is 18. The next one, 32, and so on. Now guys, if you're still not connecting with what we're doing, last time in class we figured out the energy of these energy levels, and we figured out how much energy is lost when they fall and all of that good stuff. These are the same energy levels. But what we're now going to do is talk about the idea that these electrons are not simply moving through these spherical spaces. It's way more complicated than that. So now we can get into the complications. So guys, now let's talk about sublevels. What are the 4 sublevels? S, P, D, and F, right? So how many sublevels are in the first energy level? 1, it's an S. Second, 2, S and P. Third, 3, so on, right? Okay, so guys, first energy level has how many sublevels? 1. So draw an arrow. And guys, this line is going to represent that sublevel. I'm sorry it's so, well here, let me move it up a little if I can. So guys, that line represents that sublevel. So first energy level, 1 sublevel. What kind of sublevel is it? S, so let's label it. This is the 1S sublevel. In the first energy level. But that energy level is made of 1 sublevel. So how many electrons have got to be in the sublevel if there's nowhere else for them to be because there's only 1 sublevel? 2. So guys, both these electrons are in that sublevel. Now we're ready to talk about orbitals. Guys, orbitals are the clouds. How many electrons can go in a cloud? 2. So how many orbitals does it take to hold 2 electrons? 1. And it looks like this. Guys, that is what the 1s orbital looks like. probability of finding these two electrons. And guys, that is what the 1s orbital looks like.
Is the edge of the 1s orbital at the edge of like the highest probability or at the very edge?
It's at the edge of the...
Like the dark blue part or all the others?
turn to page 225. It's a great question, Talmadge. So if you look at page 225, you'll notice that you've got pictures, right? Up top, you've got a picture of the 1s, then the 1s inside the 2s, and then the 1s and 2s inside the 3s. Kind of like a jawbreaker, right? And then down below, you've got three graphs. And you'll notice that the way that this goes is on the x-axis in all three cases, you've got radius. So the nucleus is at the origin of the graph. But then you'll notice that that crazy psi function off to the left, that's probability. So notice what's going on is that as you get further from the nucleus, the probability of finding that electron falls functionally to zero, but it is asymptotic. It never goes all the way to zero. So the idea is that the boundary of that sublevel is defined as the place where that probability falls functionally to zero, with the understanding that it never quite gets there because in theory that electron could be anywhere. But the boundary is the point at which the probability of finding the electron is zero.
What point is that? Like, at what point do you say that like, one number is more than it's not functionally zero and then you get to that number?
Yeah, and to be honest with you, I don't know exactly where they draw that because it is asymptotic. So I don't know exactly where they draw that boundary. There must be a rule that says this is the limit. If you look at the 2s though, look at that second graph, I think the limit would be the point of inflection because that's the point where the probability starts to increase again for the 2s sublevel. So maybe it can corresponds to that without the 2s, I'm not sure. But the idea is that's literally what we're looking at is it's a series of probabilities based upon radius and probability. So does that kind of answer your question? Okay, so I've never had that conversation with a group of students ever. Isn't that interesting? I've never had the opportunity to show them what those graphs mean because it's never come up. Thanks for asking. That's good stuff. You guys good on 1s? But now guys, remember this. When we actually do this, when we are drawing orbital filling diagrams, guys, remember we will actually just draw this as a box, and we'll talk more about that later, that we actually replace these with boxes with arrows, right? But we'll get there. Okay, so now guys, second energy level. Join me up here. Second energy level has how many sublevels? 2. S and P, but be careful, and Bailey, this is getting eventually to your thought. Guys, how are the S and P sublevels different besides shape? And guys, the answer is this. Spheres are inherently lower energy than more complicated shapes like dumbbells. It's a function of entropy. But spheres are lower energy than things like dumbbells. So guys, when we draw these, we need, and this is energy. Did you guys pick up on this? This is energy on the y-axis. Energy go right, electrons falling, electrons rising. This is energy. Because when we label these, the 2s literally has less energy than the 2p. Can I share with you a really wacky thought really quickly? So guys, the lab that we just did with the spectroscopes, right? Imagine that we had an electron that was going from energy level 1 to energy level 2 to energy level 1. Gives off energy, right? Probably red, short fall. But it's going. But it turns out, guys, with better spectroscopes, you can resolve that. You can actually measure the difference in wavelength of light if an electron is falling from the 2s to the 1 or the 2p to the 1. Which one would give off more energy? 2p, yeah. And guys, the thing that you're going to find when we talk about PES next time, which one of these electrons would be easier to remove? An electron in the 2s or an electron in the 2p? The 2p is easier to remove because it's further from the nucleus. And guys, we will actually be able to measure those differences when we talk about PES next time. In PES, you can actually tell the difference between the 2s and the 2p electrons. It's some of the first evidence that we ever had that those are different. The thing that's really crazy is with PES, you can actually tell the difference between an electron that's spinning up and an electron that's spinning down. Yeah, the reason is because as these electrons move around the nucleus, if their direction of spin is perpendicular to their direction of travel, their energy is a little higher than if their direction of spin is in line with their direction of travel. Isn't that crazy? Pretty cool stuff. All right, so am I the only one that finds that kind of cool? All right, so guys, let's keep going. So 2 electrons in the s, right? We already described that. So if there's 2 electrons in the s, how many have got to be in the p in order to have a total of 8? 6. So we got 6 electrons there. Now let's play the orbital game. How many electrons does it, or I'm sorry, how many orbitals does it take to house 2 electrons? 1. It's a sphere. It's an s orbital. It's a sphere. How will it be different than the 1s? Bigger. So the 2s is bigger than the 1s. Then, guys, let's talk about the p's. How many orbitals does it take to house 6 electrons? Or wait, you're drawing. Never mind.
Wait, why is it bigger?
Because it's in the second energy level. Remember here, Alice, that the first number, the 1 and the 2 tell us the size. So it's bigger because it's in the 2s. It's a sphere because it's in s, but it's bigger because it's a 2. And guys, don't hesitate to ask questions. So now, guys, let's do P. How many orbitals does it take to house 6 electrons? 3. What do they look like? Not spheres. They look like figure 8s or dumbbells. And now, guys, we can have kind of an interesting compare and contrast conversation when you're ready. It's fun to teach this the second time to y'all because we can talk about stuff that we couldn't talk about last time. Are you done drawing so you can keep learning? Oh, good. Okay. So, guys, are we comfortable with the idea that the 2s is bigger than the 1s? Okay, now what about this? How do the 2s and the 2p compare and contrast? How are they different? Shapes, right? Spheres and dumbbells. But how are they similar? They are similar in size. The 2s and the 2p are similar in size because they make up the second energy level. The difference is their shapes. Go ahead.
So do they have the same radius?
That's a great question, and the answer is no, and let's talk. So the idea is this, talking about radius, and you got to give me some, they're not, but. So say that this is the radius of the s, and this is the radius of the p. They are close, but not exactly the same. Which one will be bigger, the p's or the s's? The p's, because they are slightly higher energy. So they're close enough that we consider them to be in the same general energy level, but the p's are slightly bigger than the s's in any energy level. Is that okay? Yeah, go ahead. That's a great question. And the answer is, remember, we're just talking about probabilities. So you have the greatest probability of finding 2 electrons in that space. But in theory, those electrons could be anywhere. But even in those spaces of greatest probability, they do jump between orbitals. So electrons can freely exchange between orbitals. They freely exchange between lobes. But even at that, they could in theory be anywhere. But this is where they spend the vast majority of their time. Is that okay? Okay. So guys, remember then the conversation that we had. Well, some of you don't remember. I shouldn't say that. Oh, poop. If I click on this, I can't clear my screen without clicking on the slide. This drives me nuts. All right, so let's just do this. So guys, we understand that these sublevels then, or these orbitals, are separated by 90 degrees due to repulsion. But guys, remember the idea then is this. This nucleus and this nucleus and these nuclei are all the same nuclei. We've dissected this for clarity, but what we're really talking about is 2, 4, 6, 8, 10 electrons all around the same nucleus. And guys, if that's the case, that makes this neon. So collapsing these all back together around the same nucleus, we then have a representation of what neon actually looks like. And it's this. And this is actually pretty good. So guys, let me change colors. Yeah, the problem is that Apple is finally giving up. I don't know if you guys know this or not. In the newest release of the Apple operating system, they're no longer supporting 32-bit software. They've been generous over the last 6 or 7 years to support old legacy software, like the software that I use to draw on my board. And they're no longer supporting it, and progressively over time it's just starting to die. So, and I can't find another option. So, guys, what is this right there? That's the 1s sublevel, the 1s orbital, 2 electrons in there, moving freely. Not, as Cody said, not always in there, but in there most of the time. Then, guys, the next 2 electrons that we see in this atom are out here. What's that? The 2s sublevel, the 2s orbital in the 2s sublevel, and those electrons are moving freely, most of their time spent there. Then, guys, we've got this. And Leah, this was to your question.
Oh, yeah.
What's that dude?
That's the 2P.
One of the 3 2p orbitals. But your word radius was brilliant, right? Because here's a radius for the 2s. Here's the radius for the 2p. And you'll notice the p is a little bigger than the s. Together, we call those the same energy level. But in fact, the p is a little higher than the s. And so that's 1, and then 2, and then the 3rd orbital for the 2p sublevel. And together, that gives us a representation of what a neon atom looks like as we bring all those together. Yep. Oh my gosh, all the time. Yeah, so they interact frequently. They have to. They're moving randomly around the nucleus. But the thing that's interesting is that their movement actually becomes less random as they interact with each other. Because, I mean, if you could just simply... I'd like to point out I didn't cuss. But it was really close. So, for example, I don't know, let's just put an electron right there. One of the 1s electrons. So now that that 1s electron is sitting there, the likelihood of the other 1s electron or the 2s and any of the 2p's also being in that space falls to 0. Because if that electron's there, no other electron can be there because they repel each other. So they interact all the time, but the sum total of those interactions is actually just a lot of pushing. And so they move within each other all the time, but as one enters, another will leave because they are repelling each other. So it's kind of an interesting dance. But that's really what they're doing. I mean, if you fundamentally, what these electrons are trying to do is they're trying to get as close to the nucleus as they possibly can and as far away from each other as they possibly can. And creating these spaces is the easiest way to do that. Yeah. You guys good on these ideas? Were you doing this or just, I thought you were going to ask a question. Yeah, you're okay? Okay, so, sorry, that was awkward. So, guys, this then is how we represent. And then maybe we can just stop this conversation and relate it to the periodic table. So, guys, notice the transition. I don't think you need to draw it. But hopefully you understand that when we represent these orbitals with the electrons in the orbitals, we don't draw the spheres or the dumbbells. We draw boxes. And the reason that we draw boxes is because we know that none of these orbitals are shaped like a box. We pick a structure that is not in any way confusing. It's a box. It's not meant to be the shape. It's just meant to stand in for an orbital. And then, guys, what do the arrows represent? The electrons spinning in opposite directions. Is that coming back to you? Okay, so guys, third energy level. Third energy level then goes like this. Be careful as you draw it. The third energy level goes 3s, 3p, 3s, 3p, 3d. But guys, notice where the 3d is. Right below the fourth energy level. And Bailey, this is where your question really comes into focus. So guys, look at what's going on. As we move out in energy levels, what's happening to the space between the energy levels? They're getting smaller. But also notice, sort of paradoxically, as the space between these gets smaller, the amount of stuff that goes in that space is going up. So we really have a coming crisis because we've got less space between the energy levels and more electrons to put into those spaces. And eventually it creates problems. So, guys, we've got the S, the P, the D. We've got 2 in the S, 6 in the P. How many then are in the D? 10. How many orbitals does it take to house 10 electrons? 5. And once you're done writing them down, I can show you the pictures. You guys ready? So the Ds actually look like this. Those are the d orbitals, again, all clustered around the same nucleus, but dissected apart so you can see them individually. And each one of these volumes represents the space that you're most likely to find 2 electrons with opposite spins paired up in the orbital. You remember all of that? Is that okay? Can I go on? Oh, yeah.
We'll just stop the photo. So one
Yeah.
electron is in like one of the four
Right.
spaces.
Yeah.
Would the other electron most likely be in the opposite side?
Exactly. They will get as distant as they can. I'm scared to death to touch my board, so I'm just going to point. Hopefully that doesn't screw anything up. So if there's an electron in there, the other one will more likely be there and not in the other 2. Yeah, they're always trying to get as far apart as they can. Yeah, James?
Oh, and the last one.
This dude, isn't that interesting that in fact actually one of these 2 electrons will actually occupy that donut-like space. Isn't that weird? So one of them will be in either one of these lobes and then the other will be in there. Yeah. It doesn't. So yeah, it actually doesn't, Alice. 4 of these orbitals are clover leaf shaped, and the 5th one actually kind of looks like the Michelin Man. You guys okay? All right. So guys, again, we draw these like so. I clicked. Do we need to go? Please don't make me go back because my computer may explode. Okay.
It's just a weird question.
Take your time. You're okay.
So these electrons are trying to get away from each other as much as possible.
True.
But they can't. But we've kind of seen that they can be like anywhere.
Right.
So why not have one electron be like at one end of the universe and the other electron at the other end, if that's
Yeah.
possible?
Yeah.
But yeah.
Sure.
So why not have that instead of just kind of
Yeah.
in that shape?
Sure. So there's 2 answers to that. One is the asymptotes that Talmage got us thinking about. That what you're saying is absolutely true. In theory, some of the electrons from the atoms that make up my flesh are in you. And I want them back before you go to lunch. But seriously, that's the case. That in theory, there are electrons from me in you and vice versa. But the problem is that when that electron gets from me to over to you, it's really so far away that it's no longer associated with my electron. It's been with my atoms. It's been ionized. So this is where you get into that weird difference between theory and practice. So in theory, mathematically, graphical asymptotes, our electrons, an atom's electrons in theory could be anywhere. Could be in you, could be, as you said, on the other side of the universe. The math would suggest that. But practically, we understand that if this electron is all the way over there, that bugger's not attracted to this nucleus anymore, and we consider that to be ionized. So the theory and the practice are two completely different things. The problem is that when you work that backwards, you then have to talk about the tension between, is an electron a thing or is it a probability? And electrons are actually not things until you look for them. Electrons are actually probabilities. When particle physicists talk about electrons, they don't talk about little marbles. They actually talk about probabilities in a field of energy. And at that point, the conversation completely changes. We're going to focus on them as if they're particles, but understand the conversation is much more complicated. Go ahead.
So how does the nucleus play into all of this? Because it's a ball of positive energy in the middle of chaos.
Yeah, be careful with energy. Yeah, positive charge. And that's the point. And we said this a second ago when we were talking about this idea, if there's an electron here, the other electrons will tend to not be there because of repulsion. And so really what we've got is we've got a nucleus with all these electrons just trying to find the lowest energy state they possibly can. And what they're trying to literally do is get as close to each other, get as close to the nucleus as they can, but as far away from each other as they can. So all of these pretty shapes and spaces that we're looking at are actually just resolution to that conflict. How do you think about it this way. If you've got something in the middle of your world that is attractive, but you've got a whole bunch of other things that are repulsive, how do you get all these things together so they can get as close to this as they can, but as far away from each other as they can? And the answer is this. That's the idea, is all of this stuff is just a resolution of tension. They're literally just trying to find the lowest energy spaces they can. And none of that would happen without the nucleus. Yeah.
Well, if so, the nucleus is attracting them all together,
Yeah.
wouldn't they all just lock at the very ends of each orbital if they're trying to find this?
Yeah, but the problem is that it's a fascinating question. The problem is if they were to do that, they would stop moving. And again, to answer your question, we've got to talk about them like particles, and they're not. They're probabilities. But we can even talk about it relative to being a particle. So if those electrons were to lock, as you said, at the ends of those things, they'd all fall into the nucleus. Right? They have to be moving. And the minute things start moving, you have to have chaos. You have to have unpredictability, and that unpredictability then necessitates that they're all adjusting relative to each other, so that couldn't happen. You guys good? Crazy stuff, right? All right, so guys, let's do this then, and then we got to get practical for a minute. Fourth energy level goes like this, and this is what Bailey got us thinking about. Guys, it really goes 4S, 4P, 4D, 4F. And guys, let's just do this. Don't write this down. Just watch. Guys, here's the fourth energy level. But we've got these third and fourth energy levels so tight together, right? These are getting really close together. And not only are they getting really close together, but this third energy level is wacky. It's all these clover leaves and Michelin Man things. Guys, these are super duper complicated. So we've got two things going on. They're closing in on each other, and these are messy. And guys, messy is higher energy, entropy, right? Messy is higher energy. And so the way that this goes is it's actually easier, and therefore favored, it's actually easier for electrons to first occupy a larger sphere than it is to occupy smaller, more complicated shapes. Consequently, these electrons go into the 4s before they do the 3d. So the order that they fill goes 3s, 3p, 4s, then the 3d, and then the 4p, and then it goes on from there. Do you remember that overlap thing? Okay. So guys, with that said, and we're not going to make it as intriguing as maybe it was before when you learned this the first time. But remember, guys, the idea is you've got to be able to figure out this orbital filling order for all the atoms on the periodic table. You've got to know 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. But we understand, right? It's on the periodic table. Did Josh and Alice, you guys are Mountain View people, did you guys connect this to the periodic table? Okay, and you did as well, right, Code? Okay, let's talk. So guys, remember the idea is that the energy levels are the horizontal rows. The sublevels are represented as the S, the P, the D, and the F. And then guys, all you have to do is read. So electrons 1 and 2 are in the 1s, then electrons 3 and 4 are in the 2s, then electrons 5, 6, 7, 8, 9, and 10 are in the 2p. Is this coming back to you? Then 11 and 12 are in the 3s, then these guys are in the 3p. Now guys, where are electrons 19 and 20? 4s, and then these dudes are in the d, but it's d minus 1, so it's 3d, and then back out to the 4p. Do you remember that? Okay. So guys, relative to this, there are, for AP, there are two ways that you need to be able to represent this. Let me jump back to my other slideshow. So guys, let's do a couple of these together. This may push us into that time between Pride and between Saint. We're going to skip the pledge. This is going to be worth doing. So guys, the tricky bit then, right? The tricky bit is you will not have an annotated periodic table on the test. You will have the one that comes off of you've seen it, the stripped down one. But can you project this structure onto it just because you're familiar with it? Okay, so with that said, guys, these are the things that you've got to be able to do. So let's talk about this quickly. They want you to understand there's a couple things that you're going to see on the AP test. You might want to include these in your notes somewhere. Guys, there's a thing called the Pauli exclusion principle. His name was actually Pauli, but Pauli comes off the tongue better. Guys, it's called the Pauli exclusion principle. Let me just give it to you in a nutshell. No two electrons can have the same four quantum numbers. That's it. No two electrons can have the same four quantum numbers. Mm-hmm. So guys, really what that means is no two electrons in an atom can have the same energy level, sublevel, orbital, and spin. Why not? They made the same electron. If nothing else, spins have got to be different. Guys, that's all the Pauli exclusion principle means. Is that if you have two electrons, the same four numbers, they be the same electron. Now guys, on rule. You actually already know Hans, but you don't know it. By this name. Let me show you. Because we're going to draw the orbital filling diagram for oxygen. Oxygen is element 8. What sublevel is it in? The 2p. Guys, let me just warn you right now. Don't screw around with the AP graders on this. I've had students that have lost points on this question on the AP test because they try to get cute and cut corners. It says draw the orbital filling diagram for oxygen. Guys, you got to start at 1s and then go 2s and then go 2p. If you're drawing an orbital filling diagram, you've got to go back to S. Guys, a couple of years ago, don't write this down, Well, here, it's actually next. There was a question on the AP test that said, draw the orbital filling diagram for copper. And some of my students said, wait, copper, that's too far. And then what they did is they went argon, and then the 4s, and then the 3d, and then they drew in this from there, and they got no credit for it. Guys, if you're being asked to draw an orbital filling diagram, you must go all the way back to 1s. So, with that said, when we go oxygen, we go 1s, we go 2s, we go 2p, then one box. What's that actually look like? What does that orbital actually look like? Small sphere. 2s, bigger sphere. 2p, dumbbells of approximately the same size as that sphere. All right, then guys, we've got 8 electrons, right? Number 1 goes there. Where's number 2 go? Paired up. 3 goes here. Where's 4 go? Paired up. 5 goes here. Where does 6 go? Says who? Hund's rule. Guys, that's Hund's rule. Hund's rule says that Hund's rule says that the orbitals within a sublevel will all partially fill before the electrons start to pair up. I think TJ likes to use the bus analogy. When kids get on a school bus, they all want their own seats. Did he talk about that? Yeah. So, guys, that's Hund's rule. So which...
Faculty and students, this is a lockdown drill. Lock light out of...
Yeah, so guys, I actually forgot this was coming, but I knew that it was coming. We're going to finish oxygen, but we're also going to talk. Guys, there's not a single person in this country. There's not a single person in this country that after there was a school shooting at their school said, oh yeah, we saw that coming. Guys, the vast majority of school shootings happen at schools just like ours. And it's the unfortunate reality of the world that we live in. So, guys, heaven forbid anything like this should ever happen here. You need to know what we're going to do. And guys, I know you're understanding that the chuckling might have been inappropriate given what's going on. But guys, if you're in my room, whether here or in lab, and if they ever do come over the announcements and say lockdown, guys, that's different than lockout. Lockout means the danger is outside. We're going to lock the doors and we're going to keep doing what we're doing. Lockdown means it's in our halls. And guys, if that ever happens, we are going to go immediately to the stockroom. We are going to put as many heavy locked doors between us and whoever that person is. And I know that this sounds really weird, but if whoever that person is makes it through those locked doors, they're going to be taking a bath in a whole lot of 18 molar sulfuric acid, and they can sort it out from there. Hello? Hey, we are okay. Everyone is safe. Yep, all of them. I do not. Yep. So, guys, I know that sounds weird, but that's actually the deal. And we should talk about this too. If any of this ever goes down and they actually asked me about this on the phone. If any of this ever goes down and you are in the hallway, guys, your job is to get into a classroom as fast as you possibly can. If for some reason you are locked out and you cannot get into a hallway, guys, your job is to not pose a threat to anybody with a badge on. You don't want to get weird because protocols have completely changed since all of these school shootings have been going down. And guys, if something weird happens, we're going to have a lot of people with a lot of military weapons running up and down these hallways, frankly, looking for somebody to kill. And so you do not want in any way to be confused with the hostile. So your job is to get on the floor and get your hands out and make sure that everybody understands that you are not a threat. And I know this is, can you believe we're even talking about this? But guys, it's amazing the amount of time that they spend now thinking about this stuff. And because there's other people thinking about this stuff, you need to understand this as well. So if you're in the hall, get into a classroom. If you can't do that, if you can, get out of the building, but make sure that you don't look threatening. If you're in my room, we're going to the stock room. You got the idea? Okay, so anyway, all of that to say. So we're not done with oxygen. Which electron is that? 6? And then 7 goes there. Where's 8 go? Now 8 pairs up like that. So guys, that would be oxygen. Now guys, what about this? And you know enough to know this can't happen. What if we were to go oxygen plus 1? Which electron comes off? This guy, the one, it's literally, it's opposite the order they go in. So this would be plus 1, this would be plus 2, this would be plus 3, that would be plus 4, and so on. You remember that stuff? And guys, this would be plus 5, this would be plus 6. What about plus 7? You can't, because you can only touch these outermost electrons, which we call valence electrons. You remember that stuff? Is that okay? Okay. So guys, the other thing that you need to be able to do are what are called noble gas abbreviations. This is the place where you can start to play with this. So for example, if we do the noble gas abbreviation for copper, copper is right here. To do the noble gas abbreviation, you're going to go back to, do you remember that? You go back to argon, and then in addition to argon, we're going to have these 2 electrons that are in the 4s. And then we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. And those are in the 3D. You actually have to go back. So if you're doing the noble gas abbreviation for a noble gas, you have to go back to the previous noble gas. You guys okay? I know that drill sort of took all the fun out of this. You're good. So guys, what about this? What if we were going copper plus 1? Careful. Guys, it's this electron that comes off. Remember, the idea is that the valence electrons are the highest S or P. The Ds are never valence, right? The Ds are never valence. They're not on the outside. They're higher energy, but they're smaller. And so consequently, it's always the highest S's and P's. Is that coming back to you at all? Is that okay? Questions or things y'all want to talk about? We're good? Okay, yeah.
I don't understand why you're adding a 1. Like, where does that?
I just made it up. I just said, what if copper was plus 1? The important understanding, though, Alice, is when these elements like copper lose electrons, where do they lose them from?
Oh, okay.
And the answer is, so what about this, guys? What if we wanted to go copper minus 1? So this should be a 2, right? What if you go copper minus 1? You can't. Yeah, copper can't be negative because it has nowhere to put the electrons, because it can't put them in the Ds. It doesn't have a P, and the S is full. Is that coming back to you? Okay, so guys, here's your homework. I frankly don't know if I can let you go right now because